Поехали. Так,
Спасибо.
ну что ж, давайте начнем. Вот сегодня у нас выступает Григорий Геннадьевич Амосов. Доклад называется «О вероятностных операторно-значных мерах, основанных на фреймах». Just in case I repeat the same in English. So our today's speaker is Grigori Amosov, and the title of his talk is on probabilistic operator valued measures based on frames. Пожалуйста.
Thank you. I suppose that I also should speak English, maybe, I don't know. Anyway, there is no reason, there is no difference for me what language to speak. Every language for me is difficult. Uh, The topic of my talk is to compare two different tasks in analysis. First, I would like to start with the resolutions into elements of resolutions of operators, and this is one of the most popular tasks in quantum information theory. Suppose that we have some state, and this is the same as a positive operator with unit trace, and in Hilbert space H may be finite dimensional or infinite dimensional, and I suppose that we have several possible states, and somebody named Alice transmit these states, for example, rho x a to some maybe composite system in the quantum cryptography, but in this case I think that to some other system, and somebody named Bob likes to recognize what kind of state was transmitted by Alice. And for this, he can use some operator value to measure if states indexed by x from some measurable space x capital, then we can construct a measure on x with values in positive operators in the Hilbert space H. And I suppose that this is a probabilistic measure. That means not only countable additivity, for which takes place for all possible countable sets with zero intersections, pairwise zero. And I mean that this equality can be recognized through scalar products, such that if we take m of the sum of over j psi eta equals the sum of j bj, oh sorry, psi eta, and in this sense the convergence can be recognized in this sense. And surely on the empty set we have 0, and for all space X, the identity operator. And all these positive operators satisfying the equality that this operator lies from 0 to the identity operator. This operator is named effects. I will be interested in the case of discrete alphabet X, such that X, for example, goes 1, 2, 3, n, and n less or equal the infinity. In this case, Bob measure this state that was transmitted from Alice, and he obtained a probability distribution of the form place rho m, for example, x. This means that this is a probability that can be attributed to the case that rho transmitted by Alice was equal to rho x a. And the main question is to construct a measure that allows us to reconstruct this rho that was with the very smallest possible error. And why we need anyway, if we have two projections, orthogonal projections, for example, P equals psi1, psi1, and P1 and P2 equals scalar product of this kind with unit vectors psi1 and psi2. Then we can end the inner product psi1 and psi2 equals 0. Then we can easily, without any error, recognize what kind of state was, because we can put m from 1 equal E1 and m2 equals E2. And I suppose that in this case we need only two-dimensional Hilbert space to take our measure. And why we don't use this opportunity? Because we have a possibility that due to some reasons we have the third part, so-called F, and she also like to know the state was transmitted by Alice. So we can suppose that Alice, for her reason, can use non-orthogonal states for example, as follows: two states with some angle from these two states. And then we can construct our measure in other way. For example, we can take orthogonal system. We can take это one orthogonal to это two, and это two orthogonal to psi1. And we can take two projections, Q1 and Q2. Such that we have not here the no, the normalization condition of this kind, such that yes, here we have m of 1 plus m of 2 equals the density operator. Here we have not this kind. Nevertheless, we have that P2 1 equals 0. Yes. And P1 to 0. So this case is optimal for our distinguishing between two states. Nevertheless, we have some three operator. Anyway, we have the following picture. If you have two not orthogonal vectors, then there exists the third vector, not normalized maybe, but anyway, there is the third vector such that if you take the sum, there exist three numbers, alpha, beta, and gamma, such that this sum equals to the identity operator. So we have some operator valued measure. The most popular and known case with equiangular values 2 pi over 3. In this case, this coefficients is known to be 2 over 3. So we can translate these ideas to any case of discrete measure, and our goal is to construct some measure with mm, good with good properties for distinguishing states. And one of these approaches goes to the infinite dimensional case, and I will discuss it later. Now I would like to say a few words about frames. Frames. We can take such vectors, frames in a Hilbert space. We can take such vectors that the scalar products of the form satisfy the known inequalities. If it is so, then Fj is said to be a frame. If E capital equals B capital, a tight frame. And if E capital equals B capital equals 1, a Parseval frame. Why I need the last equality? Because one of my tasks in this area is to find a number of projections like here that satisfy this equality, that allows us to define a measure, an operator valid measure normed to the identity operator. And we can take projections corresponding to Fj. Normally, Fj not are linear independent ever in the case of Parseval frame, because if you take several frames, for example, if you have several orthonormal bases, and you can take several orthonormal bases, each of these bases satisfies the condition for a Parseval frame. So the union is also a Parseval frame. And so you see that if some frame is Parseval, it's not it's not it doesn't follow that these vectors are independent, are linear independent. So I can take some operators, for example, because we have not any conditions for Fj to be unit. So if they are not unit, you need to construct projections in other way. For example, like F, the inner product of F, J, Fj square, Fj, something like this. And you can try to construct measure with from the condition m of j equals, for example, alpha j e j. And you can try if j runs over all x, you can try to put alpha j, pj equals the identity operator. And this normalized condition can be, it is possible to check when this condition is satisfied. And surprisingly, we have the following situation. Maybe not a theorem, but rather proposition. Proposition. If fj is the Riesz basis, then only if only ой, only if uh, fj is the orthonormal basis. And this is very interesting thing because Cadison-Zinger problem, Zinger positively solved Cadison-Zinger problem implies that any Bessel fj is a union of finite number of the Riesz. So if we like to if you like to construct a measure with with the normalization condition of the form it of the form m of x equals to the identity operator, then we have that you can try to divide your vectors into finite number of Riesz sequences, and we can see that you cannot normalize this formula. Nevertheless, it's not so bad because if we try to construct measure from frames here, then you can take you can pick up alpha j. Maybe I go to other page. We can pick up alpha j such that alpha j pj less or equal the identity operator. And so you can construct a measure in such you can construct a measure on x plus empty set, for example, such that m of x equals pj, while m of empty set, maybe not empty set, it's not so good idea. Special element on this special element we have the identity operator minus the sum of j. And so we have some measure, and you can do something with this measure. And now I would like to go to one special case of this construction, especially about coherent states. If you take this is a very well-known fact from the signal theory, and maybe appearing about 1946 due to the works by Gaber. Nevertheless, it is known also from our part of science, namely quantum mechanics, and from also very old time of Schrödinger and so on. If you take such, such vectors, with unit norms, this is so-called coherent states. And due to very well-known formula by Glauber Sudarshan, we have that projections, if you take projections, we have the identity operator, and this formula, very well-known formula, shows us that we can construct a measure, operator valued measure, with operator valued, not operator valued, but measure with operator with projection valued density and some coefficient, scalar coefficient. we can define such a measure, the Glauber-Sudarshan measure, this kind. Oh, sorry. For any measurable subsets B of the complex plane. Then we can ask ourselves, is it possible to take some of these operators with these projections from this formula such that uh, we can save the basic properties of the measure. This is very natural question, and it was stated for coherent state. It was stated by Askold Переломов. In 1971. And he considered such a task. He take parallel lines in complex plane with some determined by some complex numbers in this plane, even with some step, with some step, depending on the the modulus of alpha and beta. And it appeared that these vectors, psi, alpha, psi, sorry, maybe not psi and f. These vectors for this set with nodes here, these vectors is complete if beta pi. In the theory of Gabor, here we have one. This is because different definition of this coherent states with some factor pi. It's very interesting that although very old results, it was not recognized whether this number of coherent states, whether this is frame. Is this condition satisfied or not? It was not no, and its results. This result appeared later, and due to Yuri Lubarsky, Christians say. These two works are independent. About 1992, that if these two vectors strictly less than pi, then this is a frame. Then you can define so-called displacement operators of the form displacement operators oh, sorry. Q and pi. Sorry. Maybe I will use other notations for my convenience. These unitary operators into R, and you can consider such operators or projections. And here P0 is P0 is a projection on coherent states for states F0. And the same thing as was for coherent states can be reformulated as whether it is true that E, E, equals the identity operator, or maybe not all. Here we can take not all projections, but only several. This is the same. Nevertheless, such an approach allows us to put here other projection. And for other projections, it's quite a different task. And such projection. And in this form, this task exists at the moment. For example, I know very interesting paper by Anton Baranov and Yuri Belov about this case, and in this paper of very recent paper, maybe 2 years ago. Here they put the sectant, the projection on the sectant, and it's very interesting paper, full with some interesting analysis. Moreover, I said here about, sorry, position. Lost. Oh, and this result is also from our paper with Anton Baranov, and we like to continue this research, and also I would like to concern to the case about how can be described information complete measures. Complete measures. I mean that some measure is information complete if you take some states, positive operator with unit trace, and if you take trace from our measure from on some set. Suppose that this is a zero, and the question is it possible? Maybe it's better to say in other form. Is it possible that well, this two probability distribution can coincide on two different states for all measurable states, all measurable sets B. If from this equality immediately follows that ρ1 equals ρ2, this measure M is said to be informationally complete. How to construct informationally complete measure? We can we prove the following theorem. If U sub j is complete in some Hilbert space H consisting of vectors of Hilbert space H, then I can construct a new set of vectors in the form U sub j plus U sub j plus U sub k plus U sub j imaginary unit. If you construct our measure with projections with projection value density from this set of elements, then this number generates and informationally complete measures. Unfortunately, we cannot apply these results to coherent vectors because the sum of two coherent vectors are not coherent, is not coherent vector. So here we have some superpositions of coherent vectors, and it doesn't uh, does not give us anything. So although I know how to construct measures uh, frames, I don't know whether it will be complete, information complete or not, and so on. I suppose that this is all that I like to say. Thank you for your attention.
Thank you very much for your talk. Questions, please.
Yeah, I have a question concerning that proposition. You were trying to generate the measures from frames,
Yes,
and suddenly you said that it's a Rees basis.
yes.
But it's supposed to be a frame, right? I don't know what is my Rees basis.
Oh,
Can you
okay.
explain this?
Only definition. I see. Just a moment. If you take some operator bounded with bounded inverse, you can construct a new basis from orthonormal basis. T, E, J, if E, J orthonormal basis and T and T inverse T bounded in a Hilbert space, then this number of vectors is said to be the Rees basis.
Ah, so it's a frame, right? In some sense.
It's one kind of frame, of course, because here we have a dual frame. We have some vectors also being there is basis such that we have some kind of duality. And so this is also Rees basis, and there exists this basis. Nevertheless, if f sub j is a frame, then these vectors are not independent,
Yeah.
linearly independent. But it follows from the Cadison-Zinger problem, positively solved, that all frames can be divided into the sum of the Rees sequences, not basis, because all these Rees sequences is the basis in its envelope. In its envelope, not in the whole space, but in its envelope. Nevertheless, we can divide it. Arbitrary frame can be divided. J, Pj1,
Mhm.
Pj k, we finite k, such that all these sequences are Rees.
Yeah. Okay. Okay. I see. Okay. What about those coefficients alpha j? Can you find them, or You're just saying that
Yes, yes, yes,
there are
it's
this
possible to
model.
find. Anyway, if this is a least basis, of course, this is a very really a dual sequence can be demonstrated by means of the beginning of my talk here. You can not here. Here. Here you construct, really you construct a bi-orthogonal system in quantum cryptography. You can take two not orthogonal vectors and the vectors orthogonal to each from this. This is a dual number of vectors.
I see. Mhm.
And here,
Okay.
for this very small dimension, here we have a very easy picture with this measure. Here can be constructed in the evident form. All constructions are evident.
Okay, okay. Yeah, thank you. Mhm.
Спасибо за вопрос.
Mhm.
Еще вопрос, пожалуйста.
I have one question. So thank you for your very interesting and informative talk. What kind of benefits one can expect in, for example, quantum tomography or quantum measurement? Can we reduce the number of like measured values by using these frames, or could you comment?
I don't know. Really, if we have infinite dimensional space, surely it's not so applicable in the practice. It's interesting to obtain some answers to our questions, how it works. Immediately, I don't know what benefit can be done here.
Mhm.
Nevertheless, there are many, many questions that have no answers here.
Okay, thank you. Allow me to ask one more question. You mentioned the papers of with Baranov or Belov. So could you mention what kind of topics in those papers were discussed?
This paper can be taken from archive. It's quite easy. Below
Okay.
Baranov and the easy searching procedure
Mhm.
will provide you this paper.
Okay, good. So, what was the original, topic of those papers? Are they also covering these frames or some other topics?
Oh, this is, I am sure that mathematics
Mhm.
in archive. Nevertheless, I cannot, I don't remember.
Okay, I will check. Thank you.
Maybe about frames, something
Mhm.
like this.
Mhm. Thank you.
More questions, please. Okay, so if there are no more questions, we thank speaker. Большое спасибо.
Спасибо.
Вот очень интересно, как всегда.
Спасибо.
Спасибо большое. До свидания.
Ну что ж, тогда до встречи через
Спасибо.
неделю.
Спасибо. До свидания.
До свидания.
До свидания.
До свидания.